Okay, carrying on with the 2017 Oxford Pat. So we got up to question 13 after a pretty easy set of multiple choice questions. I'm sure it's going to ramp up at some point because it always does. So expand this as a sum of powers of x. Okay, right, let's do our usual systematic approach to this. So we need our fifth row of Pascal's triangle. So that's the 1, 5, 10, 10, 5, 1 row. Then we're going to have 3 to the 5, 3 to the 4, 3 to the 3, 3 to the 2, and then 3. And then starting from the bottom, we'll have 2x to the 5, to the 4, to the 3, to, let's make that look more like a 3, and then 1. So we just need to put all of these in. So what's 3 to the power of 5? That's going to be 9 squared times 3, 381, so 243. Then we're going to have, so we'll have 5 times 2 times 81, so 810x. Then we're going to have 4 times 27 times 10, so that is 4 times 270, which is 1080. And we're up to x squared now. Then we're going to have 90 times 8, which is 720 x cubed. Then we've got, what's that, 16 times 15, so that's 240 x to the 4. And then we've got 32 at the end for x to the 5. So just write that out in, 32 x to the 5 plus do all the way along, and then you got your answer. All right, not bad. A lot of work for 3 marks, but it's easy work. Question 14. Person A is busy for 50% of the week, person B for 75%, person C for 20%. Pick a time at random. What's the probability that they're all busy? So if they're all busy, well, that's half of the time for A, 3/4 of the time for B, and 1/5 of the time for C. So that is 3 over 40. So, well, let's put it back into percentages because, put it back into the format of what they were saying. So 3 over 40 is, what's that? 1 over 40 is 2.5%, so 7.5%. All 3 can attend. Right, so we just got the reverse of all of these. So we got 1/2 times 1/4 times 4/5, which is going to be, well, the 4's cancel, so we got 1 over 10, which is equal to 10%. Right, they're still sticking easy questions so far. 15. A spring with spring constant K, natural length L, joins 2 blocks of mass M and M. 2 blocks lie on a horizontal table L apart. Right, let's get all this. So we got a little one, M. We got a big one, M. We got this spring going between them. They are initially capital L apart. Right, the maximum force for static friction is, right, okay, so we're using that as our coefficient of friction. Okay, how far must the mass big M be displaced to cause mass M to move? Right, so we're moving this off to the side, which means we're going to have our static friction here, which is going to be mu s times little mg, and we're going to have some force going here. So we need the F, which is equal to, what are they, spring constant K, so Kx, because we're wanting to move it by an amount. That needs to be greater than mu s mg. So x has got to be greater than mu s mg over k. Another 5 marks for that. Now we've got cone has equal height to the diameter of a sphere. Right. The volumes of the 2 objects are equal. The radius of the sphere is r. What is the radius of the base of the cone? So we've got the, well, the volume of the sphere is 4/3 pi r cubed. So that's good. And that is equal to volumes are equal. What is the radius of the base of the cone? Right, so the volume of a cone is 1/3 pi x squared h. And what have they said about h? The height is equal to the diameter. So we need to multiply that by 2r. Okay, and we need to cancel lots of things. So we get rid of the pi's, get rid of the thirds, get rid of one of the 2's, get rid of one of the r's. So we've got that x squared is equal to 2r squared. So x is equal to r root 2. So yeah, I mean, that's fine. I mean, most people know the volume of the cone, I think. I mean, if you don't know volume of a cone, it's very easy to work out if you can do volumes of revolution. So you set up a straight line, which has got, you know, some kind of height. This is going to be the r. So we're rotating this line around the x-axis. So it's got to have our radius at the base there. This has got to be h, the x-coordinate coming up to here. And then we can rotate this around. So the equation of the line is going to be, it's going through the origin. So we don't have a constant. We just need the gradient, which is going to be r over h. So that is our y. And then the volume of the cone is going to be the integral from 0 of h. It's like we're splitting them up into little discs. So it's going to be pi y squared dx. So it's every little disc has got a width of dx. It's got a radius of y. So we've got pi y squared times dx. We just integrate all of that. Of course, y squared. So that then becomes the integral of 0 to h of pi r squared over h squared x squared dx. So we've got, that's going to be equal to what, pi r squared over h squared, and then h cubed over 3. So we cancel those with that, and then we got pi r squared h over 3. So it's a very easy one to show, but most people, I think, remember that one, I think. So let's push on. Question 17. Parachutist jumps out of a plane at height h. She is subject to air resistance with a force of that. The equation of motion is given by that. What are the units of alpha? Right, so these are all forces. So we're going to have, so for alpha v squared, then we've got so the units of that have got to be kilograms, meters per second squared. We've got meters squared per second squared, so we're going to have kilograms per meter. So alpha is in kilograms per meter, just to get the units to add up. Estimate how much work is done by the air resistance as she falls, assuming she is falling near terminal velocity by the time she reaches the ground. Right, so that means, what have we got here? So by the time you get to the ground then, so we've started off with mgh, that's our starting energy. And when we get to the ground, then we are going to have a half m terminal velocity squared. So in this case then, so our terminal velocity is going to be when we've got no acceleration. So for terminal velocity, we're going to have that mg is equal to alpha vt squared. So we've got that. Oh, well, that's great. So vt squared, we can just put that straight into here. Oh, this is equal to the work done. That's the change in the energy that we've got, the energy loss, the difference between what we started with and what we've ended up with. So what we're trying to work out, we just need to work this out. So we've got an mgh minus a half m times mg over alpha, which is equal to, let's factorize mg's. So we've got mgh minus, what was left, m over 2 alpha. Yep, all good. 7 marks for that. Again, this is, it's really worrying me for what the questions are going to be like at the end of this, because we haven't had to do anything yet and we're on question 18. Right, although this does look quite intimidating. Consider two sound waves traveling with the same speed and amplitude but having similar but slightly different wavelengths. Okay. Angular frequencies, yeah, what I would do. Two waves are described by these functions. Right, so it's the same thing. They've just written ones and twos for y's, lambdas, and omegas. What is the speed v in terms of angular frequencies and wavelengths? Okay. Well, velocity is frequency times wavelength. Plus, of course, we know what angular frequency is. Angular frequency is 2 pi f. So we can just replace these, and then we've got our velocity in terms of angular frequency and wavelength. So that is going to be omega lambda over 2 pi. And that's going to apply for both of them, whether we've got ones or twos. So we could have ones in there, and that will be exactly the same as omega 2 lambda 2 over 2 pi, because it said they're traveling at the same speed. So, okay, so that was fine for starters. Now they want us to sketch y1 plus y2 as a function of x at some time t. So, right, that's going to be interesting. So the variation of these two waves combined through space at a fixed time. Right, and then if you stood in the path of these sound waves, what frequency would you hear, assuming you can hear it? What is the distance between points where the sound disappears? Right, and they've given us a hint here. Right, this is certainly hit the heights of a very difficult question after 17 easy ones in this paper. Particularly if you haven't done modulations of waves. Yeah, if you haven't, this is going to be amplitude modulation. And if you haven't come across this before, this is going to be ridiculously difficult. I mean, it's going to be hard enough as it is, but some awareness of amplitude modulation is really, really going to help this when it comes to sketching this graph. But still, even if you don't have that knowledge, we'll get onto that in a minute, you can at least use this hint in order to combine these things. So if we're adding up y1 and y2, let's go through this process of using this formula that they've given. So this is going to take up a lot of space. So y1 plus y2. So we've got a 2 here, and we've got a's at the front of each one. So we're going to have a 2a. And then we're going to have cos of something, which is going to be a bit of a mess. And then we're going to have cos of something else, which is going to be a bit of a mess, but it will be very similar to the first mess. So that will make it easier. So we need to add up the arguments in these cos functions and divide by 2. So let's put the half in first of all, and then we can just add these things together. So we're going to have a 2 pi x of 1 over lambda 1 plus 1 over lambda 2. And then we're going to have, well, let's keep the minus there. We'll have omega 1 plus omega 2. And then we've got a t that we can factorize onto the outside. Just sneak that one in. Now, the second one isn't going to be as bad, because all we've done is change the sign from a plus there to a minus there. So we can put minuses in front of the omega 2s. So we're going to have a half 2x 1 over lambda 1 minus 1 over lambda 2, and then minus t omega 1 minus omega 2. So it looks like a complete mess. In a lot of ways it is. But as I say, if you've done anything with amplitude modulation before, these won't be that bad to draw out. But first of all, let's simplify a few things on this just to get it. There's not much we're going to simplify, but I'm thinking about this 2, this half we've got sitting around. So we're going to have in this, we can cancel those and get pi times x 1 over lambda 1 plus 1 over lambda 2, and then minus t over 2 omega 1 plus omega 2. And then we've got cos of much the same sort of thing. Oh, I've left the x out of that one. So pi times x, and we're just putting in these minus signs now. Minus t over 2 omega 1 minus omega 2. Right, so they've said here they want us to sketch this as a function of x at some time t. So we're fixing t. And we're more or less now, so, well, not more or less, we have actually got things in the format of cos kx plus phi, and then we're multiplying those together. So let's just scroll down a bit more. So what we're saying there is this is our phase shift here, really, phi. That's just changing our x-axis values, is changing the scaling there on the x-axis, moving it left or right. But then we've got the k here, which is going to determine the frequency of the oscillation. So because this is the multiplication, if you think of transformations of graphs, we're going to be stretching by a 1 over k factor on this. So in this case, well, that's because it's repeating. It's going to repeat every 2 pi over k is what we're going to have on this. So that's going to be what our wavelength is. So because we're just rescaling the axes. So this thing here in the bracket, well, and the pi, is going to be our wavelength. So 2 pi over k is the wavelength. And, well, we can now work out what this is exactly, because k is, well, let's simplify this. We've got pi. Let's put this into one fraction. So lambda 1 plus lambda 2 over lambda 1 lambda 2. That is our k. So we need to slot this into here, and it's going to give us our wavelengths. So we've got one wavelength. So yeah, the first wavelength. Let's go with that. First wavelength of this modulated wave is going to be equal to 2 pi divided by this. So we've got 2 lambda 1 lambda 2 over lambda 1 plus lambda 2. And then the second wavelength for the second cos function, i.e. this one over here, that is going to be 2 lambda 1 lambda 2 over lambda 1 minus lambda 2. So we've got two wavelengths that are going on here. This one is smaller because we've got a larger denominator. This one is larger because we've got a smaller denominator. Because we're adding up lambda 1 lambda 2 on this first wavelength on the denominator, and here we're subtracting them. So we've got these two different wavelengths. Now we don't know how these things are related. I mean, they've said that lambda 1 and lambda 2 are quite similar to each other, I think. Is that what they said at the start? Where we got slightly different wavelengths. So, I mean, what they describe as, what they mean by slightly different is another matter. But when you're multiplying these things together, these two cos functions, you end up getting amplitude modulation. So I'll draw that out first, and then we can think about that in more detail. So the one with the long wavelength sort of provides an envelope for the other one. So if you think of that being our long wavelength cos function, and then obviously it's oscillating between this envelope as it changes with time. Now we're just drawing it for a fixed time. So if this is the wave going through space, so is going through x at a fixed time, is going to be somewhere inside that envelope. It's the envelope that changes with time, but we fix time. And then the second cos function, which has got the shorter wavelength, that is going to be modulated by that envelope. So you're going to get a cos function, but it's going to have this variable wavelength going on, variable amplitude, I should say, going on. So you're going to try and get the same number of cycles inside each one, which isn't that easy to draw. I haven't done too badly with that there, but it's modulated. So rather than just having a straight higher frequency, shorter wavelength, but constant amplitude wave, it's now modulated by the other wave. So it's got a variation in amplitude. Maybe the way to think about this is when you're multiplying these waves together, the most simple one, I suppose, is saying that you've got a straight line of y equals 1 and you've got a cos function. So you've got your cos function doing that, and then you've got your y equals 1. Well, if you multiply those two things together, you could imagine the y equals 1 line being, well, modulated by it, being bent around it. It's like you're bending that straight line around the cos curve. And that's really what we're doing when we're multiplying these two things together. It's not very easy to see this, I mean, it's not a trivial topic as it is, modulation. But if you've never seen this before, this is very, very difficult. And, don't feel bad if you can't see how this wave is operating. It takes a long time to get used to these. And it's worth going on to graphing websites. Go on somewhere like Desmos and draw out a few of these graphs to see how they're operating. But you'll see that if you multiply, maybe do a graph of cos x and then multiply it by cos 2x and then 3x, 4x, go up to 20x, and you'll see that this wave is just going to be getting shorter and shorter wavelengths. It'll be higher and higher frequency, but you're still going to be inside this envelope of the cos x curve. So, and this is what they use in radio signals. Certainly back in the day when you get AM radio, so amplitude modulation radio. So you've got information that is then being carried through the way the amplitude is being changed. And then that can be decoded by the radio into signals that are then played out. Of course, you've got FM for frequency modulation, which is more reliable. I mean, we use that more nowadays because there's a lot of things that can mess with the amplitude of a wave, but it's a lot harder to change the frequency of the wave. So if you sent something out in frequency modulation, i.e. frequency modulation will be, so you start off doing some frequency and then you might go a lot quicker and then longer. And so you've got the same base wave, but the frequency is changing all the time. And then that is what's being decoded. So you've got different ways of modulating waves. Now, drawing this one out, as I said a moment ago, we don't know the relationship between alpha 1 and alpha 2. So how many actual cycles you're putting inside the envelope wave is open to debate. I mean, you don't want to draw too many because it's saying that they're relatively close to each other. It said that they're quite similar in value, the two wavelengths. But yeah, I mean, that's really, really difficult. And yeah, I would say if you haven't seen that before, I'd be very impressed if you were able to draw that picture, having never seen a topic on modulated waves before. It's very, very tough. So what else were they asking? If you stood in the path of these waves, right? So what frequency would you hear, and what distance between points where the sound disappears? Right. Well, the frequency that you're going to hear is the frequency associated with the shorter wavelength, because that's the thing which is changing here. The solid line is the wave that we're actually hearing. So we want the shorter wavelength. In that case, we want to have, so that will be equal to the velocity divided by the short wavelength. The short wavelength is the one with a plus on it. So that's going to be V times lambda 1 plus lambda 2 divided by 2 lambda 1 lambda 2. What is that all they wanted for that? Can't remember now. What frequency would you hear? Yeah, so that's okay. I suppose we could rewrite that without the V in, maybe. And we know that V, what did we say V was? V is omega 1 lambda 1 over 2 pi. So we could say that is omega 1, the lambda 1 will cancel. So we'd have omega 1 lambda 1 plus lambda 2 over 4 pi lambda 2. Or you could do it with an omega 2 on the top and a lambda 1 on the bottom. It doesn't really matter. But that's the frequency you're hearing, because the solid line is the wave. The importance of the envelope is it is giving us these silent points, which I think is the other thing they asked about, wasn't it? What is the distance between points where the sound disappears? So it's going to be half the wavelength of the long wave. So because the wavelength of the long wave is that, the wavelength of the short wave is that. So that's short, that is long. So we need half of lambda long, because of course this envelope is traveling from here to here is one wavelength. That's a wavelength. So we need half of the long wavelength. So the between silent points, I've used up a lot of space here, so I'm going to squeeze this on. Between silent points is going to be lambda long over 2, which is going to be lambda 1 lambda 2 over lambda 1 minus lambda 2. So that's what we've got for all of that. It's, yeah, I mean, that is really, really difficult. I think there's a case for a question like that anyway. If you see something like this and you're thinking, wow, this is really intimidating, then do the rest of the questions in the paper and then come back to it if you've got time. I know it's an 8 marker, but even if you haven't seen this before, you can still do the first part and you can still use the hint, and you can maybe have a go at drawing it out. So you might be able to pick up, say, 3 marks out of the 8 or something like that. But that is a crazy step up in difficulty from the previous part of the paper. But there you go. So I suppose it gives you something else that you've learnt from this. You know, go away and look at amplitude modulation, and particularly playing around with these graphs on a graph sketcher. You know, it's something new to look into, something a new string to your bow that you can add when you're going into these exams. I mean, maybe this will come up again. You never know. It's been quite a few years since they asked this question. Right, so I'll leave that video here now, I think, and then I'll come back in the next one to wrap up all the remaining questions.